Hey everybody, this is Mr. Charnetsky, and this is Unit 3, Lesson 2, Parallelism Preserved and Protected. Alright, let's go and get into the jump start. How would you complete the following statement? Two lines in a plane are parallel if. Well, there's a couple of things that we could say. One of the obvious things is that the two lines would never intersect. So kind of filling in this statement here. Two lines in the plane are parallel if they never intersect or cross. The other thing that we could say is that two lines are parallel if they have the same slope. And parallel lines are going to be a big focus in this lesson. Okay, so the first thing we're going to look at is after certain transformations, what is happening to parallel lines? Okay, do our segments stay parallel after a transformation, or what kinds of transformations does that occur? And really, this is going to be kind of important because we looked at this triangle that we rotated into a parallelogram last lesson. And really, to get this shape, we're going to take this original triangle ABC, and we're going to rotate it 180 degrees around this midpoint. We'll call that point E. When we do that, how do we know that we end up with a parallelogram? Okay, how do I know that AC is going to line up parallel when we rotate it around 180 degrees? It seems like it would, but we kind of need a little bit more general rules when we do our transformations. So, I'll start with translations. Under what conditions are the corresponding line segments in an image and pre-image parallel after a translation? That is, which word best completes the statement? After a translation, corresponding line segments in an image and pre-image are sometimes parallel, never parallel, or always parallel. Well, let's take a look at it, what happens. So suppose I have a line segment AB, and we do a translation. So we move it maybe up and to the right some amount. Okay, so translate it. What does that look like? Well, we have experience with doing this. So might look something like this. A prime, B prime over there. So we can definitely see that it's parallel. And it's always going to be parallel, or it's always going to have the same slope as the original image. It's never going to turn. So we might be tempted to say always. Okay. There is a special case. So what if I translate it so that it lines up with the original image? So in other words, we just translate it along the same line here. Okay. Well, technically that's not parallel. It's the same slope, but those two segments are actually on the same line. So it's sometimes. Okay. Mostly always, but except for those special times when our segment is actually on the line. So so sometimes happens when the segment, or sorry, the pre-image, sorry, the image segment is on the same line as the pre-image. Okay. All right, so let's write a postulate for this. So basically we're summing this up. So after a translation, the image segments are parallel or on the same line as the pre-image. Should say parallel to. Okay, so those are translations, and they preserve parallelism. What about rotations? So after rotation, corresponding line segments in an image and scrimmage are sometimes, always, or never. Well, let's take a look. If we have a segment and we rotate it around some point. Okay. So rotating around. Well, in most cases, obviously we're not going to be parallel. So if I turn it a little bit, or up to, turn it 90 degrees, we're not going to be parallel. Yeah, our image is going to be turned. But there is a special case, and there's a certain amount of degrees we could rotate where we'll end up parallel. And I don't mean 360 because that would put us in the same spot. But if we were to rotate 180 degrees, well, if we spin around that 180 degrees, our segment is going to end up flipped around. A prime will be over here, B prime will be over here, and we'll be parallel. So it's essentially two 90s. We'll make that parallel flipped around segment. So this is a sometimes. Okay. So only when we rotate 180 degrees. There's also something else we should note on this, just to be careful. If I have a segment and we rotate it 180 degrees, but our center of rotation is on our line, if we actually rotated 180 degrees now, well, all that's going to happen is B and A are going to flip-flop spots. So we'll end up on the same line, okay? So that won't technically be parallel. So if the center of rotation is on this pre-image segment. The image will land on the same line. So sort of like our translations. Not technically parallel, same slope, just on top of itself. Okay, so let's write a rule. After a rotation of 180 degrees, an image segment will be parallel to or on the same line as its pre-image. Okay. Last one, reflections. Under what conditions are the corresponding line segments in the image pre-image parallel after a reflection? So after a reflection, well, let's see. If I take a segment and we do some sort of reflection over some line here. Well, we have to be equidistant and perpendicular to that line of reflection. So B prime end up over here. A prime will end up over here. And very obviously not going to be there we go. Not going to be parallel. Okay, so most cases we're not going to get that, keep that parallel segment. Okay, there's only one special case, and that is if I take my image or pre-image and it is lined up with my line of reflection. So if it is parallel to my line of reflection, well then it'll reflect over here and be parallel to the pre-image. Okay, so here's the sometimes. So in general, not parallel, except for that sometimes when our line reflection is parallel to our segment in our pre-image. Okay, so sometimes is when the pre-image segment is parallel to the line of reflection the image will be parallel to the pre-image. Okay, so let's write up a postulate. A postulate, by the way, I forgot to mention this earlier. A postulate is a rule, okay? And it's a rule that we can't really prove. We're just accepting it as true. Okay, so our rule is after a reflection an image, a segment is not parallel to its pre-image unless the pre-image is parallel to the line of reflection. Okay, so now we have some rules for rotations and translations and reflections, and when do we keep parallel lines. If we think back to our original shape here, when we rotate, now we can go back and say, hey, if we rotate 180 degrees, we know that AC here AC is going to be parallel to A prime B prime, and we know that AB and AC are going to be parallel. So we know we're going to make a parallelogram after 180 degree rotation. So let's see if we keep going. So if we were to rotate 180 degrees, around that midpoint, so we know we get that parallelogram there. We could continue, we could rotate another 180 degrees on another side, and then we would end up with this trapezoid shape. And then we could keep on going. And eventually, we're going to make this tessellation pattern. So this is really just a repeated pattern. And we start to see some repeating patterns with our angles. Okay? And we know that all of our lines that we can see here are parallel because they are the result of 180 degree rotations. So these are parallel lines. We see along these horizontals. These are parallel lines. Okay. And we know that that's the result of 180 degree rotation. So the lines are parallel because we did 180-degree rotations. Does this pattern justify the theorem of vertical angles? So we proved this in the previous lesson, but now we can kind of see it again. So if we look at any of our vertical angles, so for example, these blue angles right here, you can see directly across from each other, and they are matching up and they are congruent. We can see that with the green angles and the red angles, any of those angles that are directly across from each other in intersecting lines, yeah, we can definitely see that those colors are matching. So yes, the angles match after the 180-degree rotations. All right, what other angle relationships do we see? So there's lots of things. They see these repeating patterns, and especially along like these parallel lines. So if we look at a couple of these horizontal, along a couple of these horizontal parallel lines, and if we look at one of these lines going diagonally, we can see this repeated pattern where this green angle from this corner seems to repeat itself over and over again, okay, along that yellow line there. Okay, so if we were to take these two pink lines and this yellow line, we kind of pull it out of this tessellation. We only look at that, so we can see, yes, there are repeated angles along the parallel lines. And if we take those parallel lines, these two pink lines and that yellow one, and we pull them out. Okay, so here's the yellow line. Here's the two pink lines. And we can see the same pattern. So here's our green angles here and here. Those are repeating. And these are what we'd call corresponding angles. Okay, so for example, A and E are another pair of corresponding angles. Which actually, if we look at the colors here, actually those would be green as well. Okay, so can we verify through experiment that these corresponding angles are congruent? Well, we can go to GeoGebra, and I have some corresponding angles here. So we look at these green ones, those match up. They're both 106.16 degrees. The ones next to it here in the blue, those corresponding angles match up. And here in the red, okay. So it looks like that works, and I could even like change the angles around. Still, our corresponding angles are matching up, so I can test this a bunch of times. still always going to be the case. They're these always line up there, and they always are congruent. I could test it a bunch of times, but that doesn't really prove it. Kind of gives us a for example. So we could also just take a protractor and measure these angles. So yes, using a protractor or GeoGebra, we can see that they're congruent, but it doesn't quite prove it. Well, let's see if we can use our tessellation pattern. Can we prove that these repeating green angles, so we're looking at this here and here, are they always going to line up? Okay. Well, if we look at how did we get these shapes, or how did we get these angles? It's from moving our triangles around in our tessellation pattern. And so if I take this original triangle here, let's say this is my first triangle with this green angle in the top right corner, can I move it and have it line up along these parallel lines and still get these same green angles? Well, the question is, or the answer is yes, okay? And if we just did a translation, we translate this original triangle here along our yellow line, which we call that a transversal. So moving that just up the length of itself, it's going to line up along the parallel lines because we know that translations preserve parallel lines, and we'll get that same green angle. So this is how we can use this tessellation grid to see repeated patterns in our angles. So yes. So if you take the pre-image triangle and translate it along the transversal, the corresponding angles are the same. All right. Well, let's look at some other angles that we create in this diagram. So besides corresponding angles, we also have angles that we call alternate interior angles. So for example, C and F are alternate interior angles. And we could do the same thing that we did using our tessellation pattern to determine that they are congruent. So first of all, let's see if we can measure, looking at an example. So here's our alternate interior angles. So these two green ones and also these two red ones. And we can see that no matter what, the alternate interiors, the ones that are across from each other and inside our parallel lines, they are always the same measurement. So yes. Using a protractor or technology. We can verify that they are congruent. So now we're going to prove it using a 2-column proof. So this is our algebraic proof. So I'm going to set up a 2-column statements and reasons. And our first statement, well, looking at our picture, I'm looking at angle C here. And I want to say, is there any other angle that I know is congruent to angle C? And based on corresponding angles, I know that C and G are going to be congruent. Okay, so kind of connected C to G by corresponding angles. So that's my first statement. Angle C is congruent to angle G. And my reason for that is corresponding angles. Which shows us something nice about when we prove something. So if we prove corresponding angles, I can use that in a later proof. Okay, so I know C and G are congruent. I can also say now that G and F are congruent because those are vertical angles, and we've already proven that vertical angles are congruent. So angle statement 2, angle G is congruent to angle F. Those are vertical angles. Okay, algebraically, if C is congruent to G and G is congruent to F, well, I can make a substitution here. I can substitute angle F in for angle G, and my final statement would be angle C is congruent to angle F. Wrong numbers here. Sorry. Our reasons should match our statements. There we go. So that is a substitution. Okay, and this last statement is exactly what we were trying to prove. We were trying to prove that C and F were congruent, and we did that. So algebraically, we showed that alternate interior angles are congruent. Our next set of angles are alternate exterior angles. So, for example, A and H. So angles A and H would be alternate exterior, alternate meaning alternate sides of the transversal, and exterior meaning they're on the outside of our lines here. So we can verify this by experimentation. So if we go to alternate exterior angles, so we can look at these blue alternate exterior angles. Those are A and B and G are going to be congruent, and also this A and H also congruent, and we can move things around, and all of these angles are still going to be equal to each other. So Yes, using a protractor or technology like GeoGebra and verify through experiment. But experiment's not as good as a proof. So if we look at our tessellation pattern here, so imagine we're trying to prove that this green angle, redraw our transversal here. So that green angle and this green angle are congruent, okay, or that they match up. Well, again, if we look at our original triangle here, if we did our translation like we did before, when we're verifying corresponding angles, we move it up, we get to our triangle lining up here, and then after that we can do a 180-degree rotation. It'll come around and our triangle will line up along the parallel lines, and those two green angles are going to match up because they're vertical. So there is our proof on our tessellation pattern using transformations. So after a translation, along transversal, oops, and a rotation of 180 degrees, we see that alternate exterior angles are congruent. All right, are ready for more. Angles C and E are what we call same side interior angles. So if we look at angles C and E, well, obviously those are not congruent angles. C is a big angle, E is a little angle, or C is an obtuse angle, E is a acute angle, so they can't be the same. But they might have a special relationship here. If we look on GeoGebra, so if I look at the green, this dark green angle and this light green angle, we can see that they're adding together. If we put them together, they're going to add up to be 180 degrees. And we can kind of see that since this 106.16 and this 106.16 degrees next to our same side interior angles, they're going to be supplementary. So they are supplementary. In other words, C, measure of angle C plus the measure of angle E going to equal 180 degrees. So let's see if we can prove that using a two-column proof. Kind of saw graphically how those angles next to each other are gonna make a line. Well, let's start with angle C. If we start with angle C, another angle that we know is congruent to angle C is angle G. Okay. Those are corresponding angles. And then when we see that we put E and G together, they make 180 degrees because they are on the same line. So we'll say that angle C is congruent to angle G because they, oops, I keep putting one two there. Because they are corresponding. We know that angle G plus angle E equals 180 degrees because they are a linear pair. So right next to each other, E and G are going to make 180 degrees. Well, with a simple substitution, I'm going to substitute that C into angle E. So we'll have angle G plus angle, substitute the wrong spot, not into angle E, we're going to substitute in for angle G. Sorry. Okay, so angle C plus angle G equals 180 degrees. So that's a substitution. Okay, our takeaways. So we saw that corresponding angles were congruent. We saw alternate interior angles were congruent. And we saw alternate exterior angles were congruent. And finally, we saw that same side interior angles were supplementary, which means they add to 180. All right, here are our parallel postulates for translations, rotations, and reflections. We already wrote those down before, but here they are again if you need to pause and copy these down. Our vocabulary that we looked at today. And now let's talk about our retrieval. So what are complementary angles? First of all, we know what supplementary angles are. They add to 180 degrees. Complementary angles add to 90 degrees. Okay, so take a minute, find the complement for each of these given angles. So the complement to 30 degrees is 60 degrees. 60 plus 30 equals 90. Complement to 74 degrees would be 16 degrees. And the complement for 52 degrees would be 38 degrees. The supplement. Well, the supplement needs to add to 180 degrees. So for 123, that would be 57 degrees. 170, that would be 10 degrees. And for 60, it would be 120 degrees. Do all angles have both a complementary angle and a supplementary angle pair to pair them with? Well, know if the angle is more than 90 degrees, it does not have a complement. And if it is more than 180 degrees, it does not have a supplement. Okay. And that's the end of this lesson.